Hey there, my curious friend. Welcome back to Deepfield Channel. Tonight we're going to drift toward an ancient glow that has been crossing the emptiness for longer than the Earth has even existed. A galaxy so enormous that looking at it is like trying to hold something in your eyes that no pair of eyes could ever fully take in. But I promise I will try not to make this so interesting that it keeps you awake. Before we sink into this mystery though, tell me in the comments, where in the world are you listening from tonight? And if you are feeling too cozy to type much, just drop a simple hello. It might seem like a small thing, but that tiny gesture tells YouTube that our little corner here is a warm one, and it helps us bring more tired minds into this space to unwind with us. If you enjoy these scientific journeys we take together, go ahead and leave a like and subscribe. And if you're already part of this community, thank you truly from the bottom of my heart. If you want to feel even closer to what we do here, think about becoming a channel member. Members get early access to videos before everyone else. The link is down in the description. Now, wherever you are right now, find a position that feels really good. If sleep starts pulling at you, just let it. So let us begin. There is a smudge in the sky that you have probably already seen without knowing what it was. On a clear night, far from city lights, it shows up in the northern hemisphere as a faint haze, a slightly stretched blur nestled among the stars of the constellation Andromeda. Most people glance right past it. Maybe they think it is a thin wisp of cloud, maybe they do not even notice it at all. But that quiet little smudge, that whisper of light barely distinguishable from the dark backdrop behind it, is one of the most immense things that exist in the observable universe. It is an entire galaxy, and not just any galaxy. Andromeda, which astronomers refer to as Messier 31, is the closest spiral galaxy to our own Milky Way. And when we say closest, we need to recalibrate what that word even means when we are talking about cosmic distances. It sits roughly 2.5 million light years away from us. That means the light entering your eyes when you look at that smudge left its source 2.5 million years ago. Back then, our hominid ancestors were walking across Africa, still without language, without tamed fire, without any notion that there was a sky above them worth gazing at. The light you are seeing now set off before anything we would call human ever existed. That is the first thing Andromeda does to you. It dissolves time, not calendar time, not the time of stories we tell each other, but deep time, geological time, and then far beyond that, the time when the Earth was still learning how to be a livable planet, while this light had already begun its crossing. But the size of Andromeda is not just about the distance that separates it from us. That is only the beginning of what makes this galaxy so hard to fit inside a human mind. What really shifts when you start to truly understand Andromeda is not the distance, it is the extent, how much space it takes up. And here lives the biggest surprise, the property that most completely unravels what we picture when we look up at the night sky. There is a very common misunderstanding about how galaxies appear in the sky. Most people, when they think of Andromeda, picture that small smudge, maybe the size of a hazy star, something modest and contained. But that is an illusion born from our inability to see very faint light. The core of Andromeda, the brightest central part, is indeed compact and visible to the naked eye under those ideal conditions. But the galaxy itself, its true extent, its spiral arms, its halos of ancient stars and scattered gas, that real galaxy stretches across the sky over an area more than 6 times larger than the full moon. Let that settle in for a moment. More than 6 times the apparent diameter of the full moon. If your eyes could gather all the faint light Andromeda puts out, if you could see every layer of stars and gas that makes up this galaxy, it would dominate an enormous slice of the night sky. It would not be a shy little smudge. It would be an overwhelming presence, a colossal spiral structure hanging above your head every single night, waiting to be noticed. The reason we do not see it that way has everything to do with how our eyes work, and nothing to do with what is actually out there. The human retina is extraordinary at many things, but It was not built to pick up the diffuse scattered glow of a distant galaxy. Our eyes respond to contrast, to concentrated brightness. The core of Andromeda passes that test. The outer edges, the gentle spiral arms, the stellar halo stretching across degrees of sky, all of that falls below the threshold of what we can perceive. It is like trying to see smoke in a dark room. The smoke is there. Your eyes simply were not made for that particular job. Astrophotographers have known this for a long time. When they point sensitive cameras at Andromeda with long exposures, what they uncover takes your breath away. A majestic spiral with arms of young blue stars unwinding from a yellowish core of older stars, surrounded by lanes of dark dust cutting across the arms like rivers of shadow. It is an architecture on a scale that the word big simply cannot do justice to. So what is the actual size of Andromeda? The diameter of its main disk, the part where most of the stars orbit, is roughly 220,000 light-years. For comparison, the Milky Way measures around 100,000 light-years across, maybe a bit more according to newer measurements, but Andromeda is noticeably larger. If you place the two galaxies side by side on a scale, Andromeda would stretch out to something like 2 Milky Ways in extent, not twice the mass necessarily, because density and the distribution of matter are not uniform, but in pure reach, in spatial span, Andromeda is a considerably bigger neighbour. And if we factor in the dark matter halo surrounding Andromeda, that invisible sphere of mass that astronomers infer from the way stars orbit and from the gravitational pull it exerts, things get even more unsettling. The halo stretches more than 1 million light-years outward from the centre of Andromeda in every direction. Sit with that for a second. The halo of Andromeda, which you cannot see, which no optical telescope can directly show, already begins to overlap with the halo of the Milky Way. In that sense, the two galaxies are already touching. They are already intertwined at their invisible edges, long before any visible collision takes place. That fact dissolves another popular belief. We tend to say that Andromeda is approaching us, as if it were some far-off future event, but in a subtler sense the encounter has already begun. The outskirts have already met. What still lies ahead is the plunging of the cores, the tangling of spiral arms, the spectacle of stars and gas crashing together that will unfold about 4.5 billion years from now, a span of time that exceeds any human capacity for imagination, but which, from the universe's point of view, is just the next thing to happen. Andromeda holds approximately 1 trillion stars. 1 trillion. The Milky Way has somewhere between 200 and 400 billion, based on current estimates. So Andromeda has at least 2 to 3 times more stars than our home galaxy. Each one of those stars is a sun, or something resembling a sun, or something entirely unlike any sun we have ever known. Each one traces its own orbit around the galactic centre, taking hundreds of millions of years to complete a single revolution. Each one pulls and is pulled by its neighbours in a gravitational dance of such complexity that no human computer could simulate it perfectly. The composition of Andromeda is not just dust and stars, although there is enough dust to hide entire regions from curious eyes. There is also atomic hydrogen, spread in gigantic clouds that reach beyond the visible spiral arms. There is molecular hydrogen, packed into dense regions where gravity eventually overcomes pressure and new stars are born. There is plasma, gas heated to temperatures that would melt any metal we know, emitting X-rays that only space telescopes can pick up. There is a magnetic field, invisible but everywhere, shaping the paths of charged particles like force lines running through the entire body of the galaxy. And at the centre of all this, in the heart of Andromeda, there is a supermassive black hole. Not just one. There is evidence of at least 2 massive black holes very close together in the core, which suggests that Andromeda has already swallowed at least one smaller galaxy in the past, and the remnants of that encounter have not yet fully dissolved. The main black hole in Andromeda has a mass of about 100 million times the mass of our Sun. For comparison, the black hole at the centre of the Milky Way, called Sagittarius A star, has about 4 million solar masses. The heart of Andromeda is roughly 25 times more massive than the heart of our galaxy. That means Andromeda, in this regard, is a galaxy with a more violent and massive core than ours. Not necessarily more active today, because supermassive black holes spend most of their lives in relative quiet, without enough material falling onto them to produce the luminous display we call an active galactic nucleus. But the scale of the mass confined there speaks of a history of accretion, of swallowing, of growth that left permanent marks on the geometry of everything around it. The spiral structure of Andromeda has two main arms, winding outward from a central bar of stars and gas like the arms of a whirlpool frozen in light. Around those main arms there are fainter structures, fragments of additional arms, arcs of stars that look like scars from old encounters with satellite galaxies that Andromeda absorbed over billions of years of history. The galaxy is not still. It is an organism in constant transformation, just on a timescale so vast that from a human perspective it appears motionless. The satellite galaxies of Andromeda are also part of its real size. There are dozens of smaller galaxies orbiting around it, some of which are visible through amateur telescopes. The most notable among them are Messier 32 and Messier 110, which show up as diffuse smudges near the core of Andromeda in long exposure photographs. These satellite galaxies are not passive decorations. They actively participate in the gravitational dynamics of Andromeda, gently tugging at its edges, feeding gas and stars into the outer halos, and slowly accumulating material that will one day be absorbed into the larger body. It is in this process of slow absorption that one of the quietest and most powerful forces shaping the visible universe resides. Gravity working not through explosive collisions but through embraces that last entire ages. Gravity is the force that holds Andromeda together. But saying that is almost an understatement, because the gravity that keeps a galaxy coherent is not the same experience you have when you drop a glass and watch it fall. It is something of an entirely different order, operating over distances that make any everyday intuition useless. To feel how this force works at a galactic scale, you first need to let go of the idea that gravity is something big things do to small things. In a galaxy, everything pulls on everything, and the result is not a fall toward a single point, but an orbital dance in which each star finds the path that balances the pull of billions of others. Picture yourself standing in a circular plaza, surrounded by millions of people also walking in circles around you, each one at a different distance from the center. None of them is falling toward the middle. Each one moves fast enough that the curve of their path matches exactly the curve created by the gravitational pull of all the mass present there. That is what happens with every star in Andromeda. The balance between orbital speed and gravitational pull is what turns a cloud of matter into a stable spiral. That balance was formalized by Isaac Newton in the 17th century, when he proposed that the attractive force between two bodies is proportional to the product of their masses and inversely proportional to the square of the distance between them. It was a law derived from watching planets orbit the Sun and the Moon orbit the Earth, but its beauty lies in the fact that it applies equally to a star at the edges of Andromeda, orbiting the galactic center, tens of thousands of light-years away. Newton had no idea he was writing an equation that would one day describe galaxies. He probably did not even imagine galaxies existed. For centuries, Newton's law was enough to describe the behavior of visible matter, but in the 20th century, when astronomers started measuring the orbital speeds of stars at the edges of spiral galaxies, something did not add up. Stars in the outer regions of a galaxy like Andromeda should orbit more slowly than inner stars, which is what you would expect if most of the mass were concentrated at the center. But what the instruments showed was different. The outer stars were orbiting at speeds nearly as high as the inner ones, as if there were far more mass out there than telescopes could detect. Vera Rubin was the astronomer who cemented this discovery definitively in the second half of the 20th century. Working with astronomer Kent Ford and using a spectrograph that Ford had developed to measure light shifts with unusual precision for the era, Rubin applied the Doppler effect to the emission lines of spiral galaxies, The Doppler effect is that phenomenon you know from sound. When an ambulance approaches, the pitch sounds higher, and when it moves away, it sounds lower, because the sound waves get compressed or stretched by relative motion. With light, it works the same way. Stars moving toward us have their spectrum shifted slightly toward blue, and stars moving away toward red. By mapping those shifts across the disks of spiral galaxies, Rubin and Ford produced rotation curves that should have dropped off progressively at the edges, the way the speed of outer planets around the Sun drops compared to Mercury and Venus. But the curves stayed flat. The orbital speed at the edges did not decrease. That could only be explained if there were an enormous amount of mass distributed in a halo around the visible disk, mass that telescopes could not see because it did not emit, reflect, or absorb light in any way detectable by the instruments of the time. That invisible mass came to be called dark matter, not because it is dark in a visual sense, but because it remains obscure to every electromagnetic instrument we have built so far. Andromeda has a dark matter halo that extends far beyond its visible disk, possibly more than 1 million light-years from the centre, merging with the equivalent halo of the Milky Way in a region of gravitational overlap that already begins connecting the two galaxies in a very concrete sense. Dark matter is not the only ingredient needed to understand how Andromeda works as a system. There is also gas, the primordial ingredient of all stars. Andromeda contains enormous reserves of molecular and atomic hydrogen, distributed along the spiral arms and in the regions between arms, this gas floating among the stars like air between the trees of a forest. When this gas concentrates beyond a certain threshold, gravity starts to overcome the internal pressure keeping it diffuse, and it collapses into ever smaller structures, fragments, heats up, and eventually ignites the nuclear fusion processes that turn hydrogen into helium and release energy as light and heat. Nuclear fusion is the energy source of every star in Andromeda. In the core of a star like the Sun, the temperature and pressure are so extreme that hydrogen nuclei fuse to form helium, releasing a tiny fraction of the original mass as pure energy, according to the relationship Albert Einstein discovered in the early 20th century between mass and energy. That relationship says that a quantity of mass equals that same mass multiplied by the square of the speed of light, an extraordinarily large number. That is why even the conversion of a minuscule amount of mass into energy produces a glow capable of lighting an entire solar system for billions of years. Andromeda has about 1 trillion stars, each one a nuclear fusion reactor converting hydrogen to heavier elements over the course of its life. When the most massive stars reach their end, they explode as supernovae, scattering into the interstellar medium the elements they forged during their lifetimes: carbon, oxygen, iron, silicon, enriching the gas with materials that will eventually find their way into new stars and planets. This cycle, stars forming from gas, living, dying, and enriching the gas for new generations, is one of the fundamental mechanisms of any active spiral galaxy. The rate at which Andromeda converts gas into stars is slower today than that of the Milky Way. That makes it a slightly more mature galaxy in evolutionary terms, with more of its mass already locked up in old reddish stars and less in the blue star-forming regions that characterize young, vigorous galaxies. But that does not mean an absence of activity. Along the spiral arms there are regions of ionized nebulae, where gas is lit up by ultraviolet radiation from young, massive stars that were recently born from the collapse of molecular clouds. These regions glow red in long exposure photographs, the characteristic red of hydrogen heated by the radiation of nearby stars. The spiral geometry of Andromeda is not accidental or decorative. It is the result of density waves propagating through the disk of the galaxy like ripples across a pond. But instead of disturbing the surface of water, these waves compress the interstellar gas as they pass through it, triggering the formation of new stars. The regions where the gas is most compressed by the density wave are exactly where young, bright stars form, and because those stars are blue and luminous, they light up the arms and make them visible from far away. The spiral arms are not fixed physical structures that stars pass through like cars on a circular track. They are wave patterns, like a traffic jam that exists at a particular stretch of highway, regardless of which specific cars are in it at any given moment. This theory was developed in the second half of the 20th century by astrophysicists Chia Chiao-Lin and Frank Xu, who formulated mathematically how periodic gravitational disturbances could propagate as density waves in a galactic disk, keeping the spiral structure coherent over immensely long stretches of time. Before that formulation, it was a puzzle why spirals did not wind up and fall apart over time, since the inner parts of a galaxy orbit faster than the outer parts, and any physical structure would wrap around itself within a few orbital cycles. The answer was that the spiral pattern is a wave, not a material structure, and waves can persist as long as there is energy to sustain them. There is a fundamental imbalance that keeps all of this in motion. A galaxy like Andromeda is not in perfect equilibrium. It is constantly processing gas, converting matter into energy, redistributing angular momentum through spiral arms and gravitational interactions, accumulating dead stars in the halo and young stars in the arms. It is a transformation machine in a steady state, but not at rest. And the fuel that feeds this machine is gas, which comes from internal reserves and from external acquisitions, the satellite galaxies that Andromeda gradually absorbs over time. When a satellite galaxy gets close enough to Andromeda, tidal forces begin to distort it. Tidal forces are the ones that act differently on different parts of an object, stretching it toward the gravitational source. The Moon creates tidal forces on Earth that raise the oceans, but the same principle, at incomparably larger scales, stretches and fragments smaller galaxies that approach Andromeda. The material from the smaller galaxy, stars and gas, is deposited in long streams that circle around and through Andromeda, tracing faint arcs in the outer halo that modern telescopes can detect as threads of almost invisible light. These stellar streams are fossil records of past absorptions. They carry the memory of galaxies that were once independent entities and are now being slowly dissolved into the larger structure. The halo of Andromeda is filled with these streams, some of them tracing orbits that take hundreds of millions of years to complete. It is a kind of gravitational archaeology, where the present holds the marks shaped as light of what happened in a past so remote that the Earth did not yet exist when the dissolution began, and it is precisely at this scale, in this slow and continuous processing of matter into structure, of gas into star, of satellite into stellar stream, that something about the fate of Andromeda begins to reveal itself. This fate is not an isolated event. It is part of a hierarchy of structures organized inside one another. Like boxes containing boxes containing boxes, each level governed by the same laws but expressing patterns that only appear at that specific scale. Andromeda exists within a context that exceeds it the same way it exceeds each of its stars individually, and understanding that context is understanding why it has the shape it has, why its material distributes the way it does, and why certain regions of it buzz with activity while others remain in near absolute silence. The universe does not distribute its matter evenly. That is one of the most fundamental discoveries of modern cosmology, and it echoes at every scale you examine. If you could look at the entire universe from very far away, you would see that galaxies are not scattered randomly through space like grains of sand tossed in the wind. They cluster in enormous filaments, in walls and sheets of matter that border colossal voids, regions of space where almost nothing exists. This pattern has a name, the cosmic web, and Andromeda, like every galaxy, is a node within that web, a concentration of matter that exists because the space around it had the conditions for matter to converge there, and not somewhere else. The cosmic web was not planned by any of its components. No hydrogen particle in the early universe decided which filament it would live in. The pattern emerged from tiny fluctuations in the density of the young universe, irregularities so small that at the time they could barely be called irregularities. Where matter was slightly denser than average, gravity pulled in even more matter, amplifying the initial difference. Where density was slightly lower, matter migrated outward, deepening the void. Over billions of years, those microscopic differences grew until they produced the structure that exists today. Filaments hundreds of millions of light-years long, equally immense voids, and at the intersection nodes, the densest groupings of galaxies we call clusters. Andromeda belongs to one of those nodes, though it is a relatively modest one in cosmic terms. It is part of what astronomers call the local group, a collection of gravitationally bound galaxies occupying a region of space a few million light-years across. Within that group, Andromeda and the Milky Way are the two dominant members, the two gravitational centers around which the other galaxies orbit. But even this local group is just a subset of a larger structure, the Virgo supercluster, which in turn sits inside an even larger structure called Laniakea, a supercluster containing hundreds of thousands of galaxies and stretching hundreds of millions of light-years. What this means for the shape of Andromeda becomes clear when you think about how gravity acts over time at multiple scales simultaneously. Andromeda does not respond only to its own internal gravity. It responds to the gravity of every other galaxy in the local group, to the pull of Virgo farther away, to the geometry of the cosmic filament it sits in. These external influences do not determine the details of its spiral arms, but they shape its orientation in space, its speed and direction of movement, and the rate at which material falls toward it from the surrounding regions. The spiral arms of Andromeda are perhaps the most visible expression of this galaxy's internal organization, and they deserve attention because they exist for reasons that are not immediately obvious. Someone might imagine that spiral arms are formed by stars simply orbiting together, held in place by mutual attraction. But that is not what happens. If it were, the arms would progressively wind around the center over time, like pasta being twirled on a fork and eventually vanish into uniformity. The spiral arms, instead, are density waves, regions where matter temporarily compresses as it passes through them, the same way traffic thickens around a slow point on a highway, even though individual cars keep moving. The wave stays in place while individual stars pass through it and move on. That distinction between the wave and the particles crossing it is essential to understanding why spiral arms are regions of intense star formation. When a cloud of gas crosses a spiral arm, it gets compressed by passing through the higher density region. That compression can be enough to trigger the gravitational collapse of gas into smaller regions that will become stars. The spiral arms are therefore trigger zones, regions where conditions for stellar birth are amplified by the geometry of the density wave. That is why images of Andromeda show the arms bluer than the core, blue being the colour of young massive stars that burn intensely and die young. The global organisation of Andromeda, then, is not a state of static balance. It is a system in constant motion, with material circulating between the disk, the halo, and the surrounding regions, with stars being born in the arms and migrating to other parts of the galaxy over their lifetimes, with gas being consumed by star formation and replenished by material falling in from the outer halo. This cycle of matter within a galaxy has a technical name, the galactic baryon cycle, and it is one of the central processes that determine how a galaxy evolves over time. What controls the rate of this cycle, the speed at which material circulates between the different parts of Andromeda, is partly determined by the rotational geometry of the disk. Andromeda rotates, just as the Milky Way rotates, but it does not rotate like a solid object. A solid disk, like a plate, spins so that every point on its surface completes one turn in the same amount of time, regardless of how far it is from the centre. A galactic disk does not work that way. Stars in the interior of the galaxy complete their orbits faster than stars at the outer edges, in terms of time per revolution, because the distance they need to travel is much shorter. But the orbital speed, the velocity at which each star moves through space, stays surprisingly constant across much of the disk, dropping far less than expected if only visible matter were responsible for the gravity. That constancy of orbital speed with distance is one of the strongest pieces of evidence that there is matter we cannot see exerting gravitational influence across the entire disk and beyond it, Dark matter, as it is called, does not emit light, does not absorb light, does not interact with ordinary matter except through gravity. But its presence can be inferred precisely because stars at the outer edges of Andromeda orbit too fast for visible matter alone to account for. There is something else out there, something immense, a halo of invisible matter wrapping the entire disk and extending far beyond the limits of what any telescope can photograph directly. That dark matter halo is probably the most massive component of Andromeda in total terms, and it is what gives the galaxy its real gravitational influence over the space around it. Dark matter is what allows Andromeda to hold its satellite galaxies in orbit, what keeps the stellar streams in the outer halo within the galaxy's gravitational reach, and what determines how it responds to the influences of the local group around it. The visible disk, with all its beauty and complexity, is just the surface layer of a structure that goes much deeper and weighs much more. The distribution of dark matter around Andromeda is not perfectly spherical, even though the simplest theoretical models represent it that way. More sophisticated simulations suggest the dark halo has irregularities, regions of slightly higher and slightly lower density, reflecting the galaxy's accretion history, the directions from which material was captured over time. Each absorbed satellite galaxy contributed not only its stars and gas, but also its own dark matter halo, which merged with Andromeda's larger halo and left imperfections that persist much longer than the visible stars from the absorption. There is a deep geometry in how all of this organizes itself. The thin, bright disk is aligned with the main rotation plane of the galaxy. The stellar halo, older and more diffuse, distributes in a roughly spherical shape around it. The dark matter halo, even larger, wraps everything with its invisible presence. And around all of that, the satellite galaxies trace their orbits in planes that tend to be aligned in ways astronomers are still trying to fully understand. This tendency of satellites to orbit in preferred planes, rather than in random directions, is a puzzle that challenges the simplest models of how galaxies grow and evolve. One possibility is that the satellites were not captured randomly, but arrived at Andromeda along preferred cosmic filaments, the same structures of the cosmic web that determine where the material feeding galaxies comes from. If material falls in predominantly from certain directions, it makes sense that the satellites, which also came from those directions, still carry the memory of that alignment in their current orbits. The past of Andromeda, therefore, is written not only in the stellar streams of the halo, but also in the geometry of the orbits of the galaxies surrounding it. Every aspect of Andromeda's large-scale organization, from its position in the cosmic web to the distribution of dark matter in the halo, from the orbital patterns of its satellites to the geometry of its spiral arms, is the result of processes that acted over billions of years and continue acting right now. None of these structures arrived at its current state all at once. Each one grew, adjusted, responded to disturbances, and reached its present form as a series of responses to influences coming from multiple directions and multiple scales at the same time. And there is an ingredient that would make all this organization dramatically different, or perhaps impossible to exist in the form it does, if it were not present. The patterns you see in Andromeda, the regularity of the spiral arms, the distinction between disk and halo, the way gas moves and accumulates in certain regions, are all shaped by something that acts as both an amplifier and a suppressor at the same time, something that can speed up star formation in certain areas while shutting it down completely in others. Without this ingredient, Andromeda would be a much simpler structure, maybe unrecognizable compared to what it is today. That ingredient is the galactic magnetic field, not the magnetism of a compass, not the field holding a note on a refrigerator, but something on a scale and of a nature that make those examples seem almost silly by comparison. The magnetic field of Andromeda permeates the entire galaxy, invisible, odorless, without surface and without edge, and yet present in every region where there is gas, dust, plasma, or movement of electric charges. It exists at every altitude of the disk, seeps into the halo, follows the spiral arms like a second geometry overlaid on the first, and acts on matter in ways that have no easy equivalent in any experience we have here on the surface of a small planet. The best way to understand what a galactic magnetic field does to the interstellar gas is to think of a multi-lane expressway during rush hour. Without any regulation, each car picks its own path, changes lanes at random, creates congestion at arbitrary points, and thins out traffic at others. But when there is a well-defined lane geometry, when flows are channeled by structures that force movement in certain directions and prevent it in others, the patterns change. The flow organizes itself. Density increases at certain points and decreases at others in a predictable way. The magnetic field of Andromeda does exactly that with the interstellar gas. It defines the lines along which gas can move with less resistance, and the directions in which movement is drastically harder. Gas tends to flow along field lines with ease, but crossing them sideways requires a force that is rarely available. This is not a poetic metaphor. It is a direct consequence of the equations describing how charged particles interact with magnetic fields, equations that have been tested in laboratories, in particle accelerators, in fusion plasmas, and through indirect observation in the most distant galaxies telescopes can reach. The magnetic field of Andromeda has an average intensity across the disk of about 5 to 10 microgauss. That number by itself means nothing to human intuition, but what it means in terms of physical consequences is enormous. For the interstellar gas, a field of that magnitude represents a magnetic pressure comparable in order of magnitude to the pressure exerted by the thermal gas itself. That means the magnetic field is not a weak influence nudging things at the margins of gas behavior, a slight bias pushing things in a preferred direction. It is a player with power equal to thermal pressure, to gravity at certain scales, and to the pressure exerted by cosmic rays crossing the galaxy. These four forces, gravity, thermal pressure, magnetic field, and cosmic ray pressure, compete and cooperate constantly, and the result of that ongoing negotiation is the structure we see when we look at Andromeda with eyes trained to read those languages. One of the most concrete manifestations of this competition is what happens when a cloud of gas begins to collapse under its own gravity to form stars. Without a magnetic field, gravitational collapse is a relatively straightforward process. Gravity overcomes thermal pressure when the cloud exceeds a certain mass and star formation begins. But when a strong magnetic field threads through that cloud, the collapse cannot happen equally in all directions. Gas can collapse along field lines without much magnetic resistance, but collapsing perpendicular to the field lines compresses the field itself, increasing its pressure and creating a force that resists the collapse. The result is that clouds tend to collapse first along the field lines, creating filaments and elongated structures that only then, in a second stage called ambipolar diffusion, can slowly separate the neutral matter from the magnetic field and allow the collapse to continue in all directions. Ambipolar diffusion is a process of almost unfathomable slowness. The neutral particles in the gas do not directly feel the magnetic field, but the ionized particles do. And since neutral and ionized particles collide with each other, the ionized ones transmit magnetic pressure to the neutral ones through contact. As the gas collapses, the neutral particles try to cross the field lines by slipping between the ionized ones, and that tension creates a diffuse resistance that acts like a brake. In regions of Andromeda where the magnetic field is especially strong, this brake can delay star formation by tens of millions of years compared to what would happen without a field. In other regions where the field is weaker or where turbulence has distorted and compressed it locally, the brake is smaller and star formation can happen more quickly. The star formation map of Andromeda is, to a significant degree, a map of the variations in intensity and geometry of its magnetic field. The magnetic field also plays a role in the opposite direction, as an amplifier rather than a suppressor. When shock waves travel through the interstellar medium of Andromeda, coming from stellar explosions or gravitational disturbances in the spiral arms, they compress the gas they encounter along the way. But they also compress the magnetic field threading that gas. A compressed field has more energy per unit volume, and that extra energy can be transferred back to the gas as turbulence and localized heating. This creates pockets of hot turbulent gas where the total pressure, adding magnetic field and thermal pressure, can be dramatically higher than in neighbouring regions. These bubbles of elevated pressure can prevent the surrounding gas from collapsing to form stars, creating zones of inhibition around zones of intense activity, which explains why star formation in Andromeda, as in the Milky Way, does not happen uniformly across the disk but concentrates in specific regions with spacings that follow an emergent logic from this competition of forces. What an observer equipped with instruments capable of seeing beyond visible light can actually perceive of this invisible field are its signatures. The most classic one is the polarization of starlight. When light from a distant star passes through the interstellar medium of Andromeda before reaching a telescope, dust grains along the way tend to align with the local magnetic field. These elongated grains, spinning around the field lines, absorb and polarize light preferentially. The result is that the light reaching the detector is not randomly polarized, but carries a directional signature that maps the geometry of the magnetic field along the line of sight. Space photographers do not see colors with this, but physicists who study polarization build detailed maps of the galactic magnetic field from these measurements, and those maps show that the field of Andromeda follows the spiral arms with a coherence stretching tens of thousands of light years without breaking its overall orientation. Another signature is synchrotron emission. High-energy electrons, accelerated by supernova explosions and other energetic sources within Andromeda, spiral along the magnetic field lines emitting radiation in the radio spectrum. This synchrotron emission is detectable by radio telescopes and reveals not only where the magnetic field is present, but also where it is strongest and where there is a higher concentration of energetic electrons. The spiral arms of Andromeda glow in radio with an intensity that is not random, but precisely traces the regions where the magnetic field and populations of energetic electrons coincide, creating a radio image of Andromeda that differs from the visible light image but is equally revealing of its internal structure. There is also a manifestation that requires no instruments at all, just the knowledge of where to look and what to imagine while looking. When you observe Andromeda through a moderate aperture telescope and notice the smooth irregularity of the spiral arms, the regions of brighter and dimmer glow alternating along the arcs, what you are partly seeing is the modulation of the magnetic field on star formation. The brighter regions are those where gas managed to collapse, where ambipolar diffusion reached a point where star formation could proceed, where young, hot stars illuminate the surrounding gas with intense ultraviolet. The darker regions between the arms, where the density of young stars drops, are partly regions where the magnetic field anchors the gas more effectively and delays collapse. The visual pattern of the spiral arms is, among other things, a diagram of the magnetic field translated into light, and the magnetic field is not static. It is generated and maintained by a process called the galactic dynamo, in which the differential rotation of the galaxy, where regions closer to the centre orbit faster than outer regions, stretches and winds the field lines along the directions of the spiral arms. Turbulence in the gas injects helicity into the field, creating components that point out of the disk plane and are then folded back into the plane by differential rotation. This cycle of stretching, twisting and realignment is what sustains the magnetic field of Andromeda over billions of years, preventing it from dissipating through diffusion the way a static field would in a conducting medium. The galactic dynamo is a machine powered by the rotation of the galaxy, fed by gas turbulence, and whose product is the magnetic field that in turn shapes the fate of all the gas trying to form stars. There is a circularity in this process that is deeply elegant. Stars that are born fuel explosions that create turbulence that feeds the dynamo, that creates the field that modulates the formation of new stars. Each turn of this cycle leaves the galaxy in a slightly different state than before, not in collapse or explosion, but in a slow transformation that looks a lot like equilibrium when observed from outside for a short period. But that equilibrium is an impression that depends entirely on the timescale you're looking at. In one night, Andromeda looks still. In 1 century, it looks still. In 1,000,000 years, small variations would already be noticeable. But the forces maintaining this apparent balance are the same ones that, under certain configurations, can break the symmetry with results that transform entire galaxies. The magnetic field that today organizes the gas of Andromeda so coherently along the spiral arms is sensitive to disturbances from outside, disturbances that could warp the field lines, inject unmagnetized gas into regions where the field was firmly established, or create pressure shocks so intense that the galactic dynamo would temporarily lose its ability to regenerate the destroyed field. And there is a disturbance of that scale approaching Andromeda, not in the sense that it is arriving this moment from an external source, but in the sense that the galaxy's own trajectory inevitably carries it toward that encounter. That encounter has a name, an estimated date, and a physics that astronomers study with a mix of admiration and something that can only be described as reverence before the inevitable. The Milky Way and Andromeda are approaching each other at a speed no human vehicle has ever reached, and one that the human mind can only process by translating it into numbers so large they lose any anchor in everyday life. What happens when 2 galaxies of this magnitude meet is not a collision in the ordinary sense of the word. There is no surface hitting surface because galaxies are made almost entirely of empty space. The stars of one galaxy would pass through the stars of the other like 2 swarms of fireflies crossing each other in the dark, each individual so far from its neighbours that the crossing would happen without a single direct contact. What collides, what interacts violently and immediately is everything that is not a star, the gas, the dust, the fields, and the structures of diffuse matter filling the spaces between the suns. The gas of Andromeda and the gas of the Milky Way, when they finally meet, will crash head-on with a force that will trigger one of the biggest star formation outbursts either galaxy has ever experienced. This process has a technical name astronomers use frequently: starburst, a burst of star formation so intense that it can consume in a few billion years gas reserves that would otherwise last tens of billions. The regions of highest gas density, where molecular clouds compress against each other during the interpenetration of the 2 galaxies, become stellar nurseries of a productivity unmatched under normal conditions in either structure on its own. Stars are born by the hundreds of thousands, in regions that were relatively barren before, and the collective glow of those regions can far exceed the brightness of the entire galaxy before the encounter. There are galaxies in other parts of the universe going through this process right now, and modern telescopes observe them as natural laboratories to understand what awaits Andromeda and the Milky Way, the so-called interacting galaxies, visible in long exposure images as twisted structures with arms stretching into long, curved filaments called tidal tails, are fragments of galaxies being torn away by the gravitational force of the encounter. These tidal tails can extend hundreds of thousands of light years beyond the main bodies of the galaxies producing them, populated with stars that were ejected from their original orbits and now follow trajectories that will separate them forever from any larger structure. Some of those stars become intergalactic wanderers, travelling through the void between galaxies without ever belonging to any of them. The threshold separating the tense balance of a rotating galaxy from the temporary chaos of a galactic encounter is crossed at a moment that carries no visible marker from the perspective of any observer. Inside one of the galaxies, there is no sonic boom, no sudden change in brightness perceived from within. What changes first is the symmetry of the orbits. Stars that previously traced predictable ellipses around the galactic centre begin to feel a gravitational disturbance coming from an unusual direction. A pull that is not from the centre of their own galaxy, but from an entire other galactic mass drawing near. These disturbances accumulate over hundreds of millions of years before any structural consequence becomes visible. And then, when the threshold is crossed, the response is global and irreversible within the timescale of the encounter. The core of Andromeda hides a supermassive black hole with an estimated mass of about 100 million solar masses. The centre of the Milky Way harbours our own, Sagittarius A star, with about 4 million solar masses. During the merger process of the two galaxies, which will unfold over billions of years with multiple passes before the final coalescence, these two supermassive black holes will gradually approach each other in the core of the combined galaxy. The physics governing this process is complex and still only partially understood, but the predicted outcome is that the two black holes will eventually form a binary system, two objects of astronomical mass orbiting each other, separated by a distance that will slowly shrink as orbital energy is radiated away in the form of gravitational waves. Gravitational waves are ripples in the very fabric of space-time, predicted by Einstein's general relativity and first detected by human instruments in 2016, when two much smaller black holes merged more than 1 billion light-years away and produced a signal that deformed space-time on Earth by a fraction of a proton's width. A binary system of supermassive black holes like the one that would form in the merger of Andromeda and the Milky Way would radiate gravitational waves of a very different amplitude and frequency, so slow and so powerful that no current detector could capture them directly. For that kind of signal, astronomers have developed an alternative detection method using as antennas the most precise and most punctual things nature has produced: pulsars. Pulsars are neutron stars that emit beams of electromagnetic radiation with such extraordinary regularity that the first astronomers to detect them, in the 1960s, seriously considered the possibility that they were signals from extraterrestrial intelligence before understanding the physics behind the periodicity. An isolated, stable pulsar can maintain its pulse cadence with a precision rivaling the best atomic clocks humanity has built. When a low-frequency gravitational wave passes through the space between a pulsar and Earth, it microscopically alters the distance the pulsar's radiation needs to travel to reach us. And that tiny change shows up as an equally tiny shift in the arrival time of the pulses. By monitoring dozens of pulsars scattered around the galaxy for years or decades, astronomers can use correlated fluctuations in arrival times as a gigantic detector of very low-frequency gravitational waves. This distributed instrument is called a pulsar timing array, and the scientific collaborations operating it are right now collecting data that will one day allow the detection of supermassive black hole binary systems in distant galaxies. What happens when two supermassive black holes finally merge surpasses any other singular event a galaxy can produce. The pulse of gravitational waves released in that moment of coalescence would carry energy equivalent to a significant fraction of the total mass of the two objects, converted entirely into propagating curvature of space-time. No supernova explosion, no gamma-ray burst, no galactic starburst releases energy in such a concentrated way in a single event, and yet that event would be completely silent in the electromagnetic sense. No light, no radio, no X-rays would necessarily be produced by the moment of the merger itself. It would be the most energetic event possible, and at the same time invisible to any telescope operating in the electromagnetic spectrum. Astronomers monitor the current state of Andromeda with a network of instruments ranging from ground-based radio telescopes capable of mapping neutral hydrogen emission at 21 centimeters wavelength, to space telescopes observing the galaxy in X-rays to identify regions of gas heated to millions of degrees, along with optical interferometers measuring the speed of individual stars in the core of Andromeda with enough precision to infer the mass of the central black hole. Each of these observational windows reveals a different layer of the galaxy, and the synthesis of those layers is what allows astronomers to build detailed dynamical models of its current state and its future evolution. The X-ray emission from Andromeda, for instance, reveals the presence of point sources that are X-ray binary systems, pairs of stars in which one component is a black hole or a neutron star, and the other is a normal star whose material is being accreted by the compact object, heating to temperatures so extreme that it emits very high energy radiation, before crossing the event horizon or colliding with the surface of the neutron star. the count and distribution of these X-ray point sources works as a census of compact objects in Andromeda. And that census informs stellar evolution models predicting how many black holes and neutron stars a galaxy of a given mass and composition should have produced over its history. There is also monitoring of so-called novae, thermonuclear explosions occurring on the surface of white dwarf stars that accumulate material from a companion star until the accumulated layer reaches enough pressure and temperature to detonate an explosive fusion. Andromeda is close enough for individual nova events to be detected by medium-sized optical telescopes, and the rate at which these events occur per unit of time is another indicator of the galaxy's stellar activity level. In years of systematic monitoring, astronomers have recorded dozens of novae in Andromeda per year, a number consistent with models but also offering individual cases of special interest, novae that deviate from typical behaviour and suggest unusual configurations in the binary systems hosting them. While you rest somewhere in the outer arms of Andromeda, a star is reaching the end of a process that lasted billions of years, its carbon and oxygen core having accumulated hydrogen and helium from the surface of a companion until reaching the threshold of a detonation that, in the coming days, will make that system for a few moments brighter than all the other suns in the galaxy combined. That instant of extreme brightness will travel the more than 2 million light-years separating us from Andromeda and reach human detectors in 2 million years, or perhaps it is already on its way, having departed at some point during the Pleistocene when the first anatomically modern humans had not yet appeared. The light from that event, when it arrives, will be recorded by instruments that do not exist yet, interpreted by scientists who have not been born, and added to a catalogue of phenomena that at this point in our story we are only just beginning to understand. And these phenomena do not happen in isolation. Every explosion, every merger, every wave propagating through space-time is a node in a web of causes and effects connecting Andromeda to structures far larger than itself. That web has a name cosmologists use with an almost casual frequency, as if the grandeur of the concept had been tamed by repetition. The large-scale structure of the universe. Andromeda does not float in the void like an isolated island. It belongs to a grouping of galaxies called the Local Group, which in turn is embedded in a larger structure called the Virgo supercluster, which in turn is just one filament in a map of filaments and voids stretching hundreds of millions of light-years in every direction. Understanding Andromeda without understanding this context is like studying a neuron without knowing there is a brain. The Local Group exerts on Andromeda a gravitational influence that goes beyond the simple attraction between two approaching galaxies. There are smaller galaxies positioned at angles that pull Andromeda slightly in oblique directions. There are streams of gas connecting members of the group like invisible bridges of neutral hydrogen, detectable only at radio wavelengths, and there is a centre of mass of the entire group around which all member galaxies orbit in ways we are still mapping with increasing precision. Andromeda does not move in a straight line. It follows a trajectory that is the result of all these overlapping forces, and calculating that trajectory accurately requires modelling the total mass of the group, including the dark matter surrounding each member galaxy like an invisible massive halo. Beyond the Local Group, the Virgo supercluster exerts a pull that acts on even larger timescales. The gravitational centre of that supercluster, a region of extraordinary density where a number of galaxies gathers that makes the Local Group look like a quiet neighbourhood, pulls our entire local grouping with a force astronomers call the Great Attractor. This pull is not immediate in the everyday sense. It manifests as a secular drift, a gradual deviation in trajectory that accumulates over tens of billions of years. Andromeda feels this tug the same way the Milky Way does, not as a sudden jolt but as a gentle tilt in the geometry of space in a specific direction. At this scale of external forces, the distinction between what is inside Andromeda and what is outside it starts to dissolve. The dark matter halo of Andromeda extends over distances so large that it already partially overlaps with the dark matter halo of the Milky Way. There is no clear boundary where one ends and the other begins. There is only a transition region where the influence of one galaxy gradually gives way to the influence of the other, and it is in this zone of interpenetration that the most sophisticated computational models work to understand how the future merger will truly begin, long before any visible collision of stars or gas. And here we reach one of the most honest frontiers of modern astronomy: the distinction between what we know and what we can predict. The models of the merger between Andromeda and the Milky Way are remarkably robust in their general predictions. The collision will happen. The result will be something astronomers call an elliptical galaxy, a galaxy without spiral arms, with stars distributed in a rounder shape, and with much less gas available to form new stars. This prediction emerges from countless independent simulations and comparisons with elliptical galaxies observed in the universe, which are believed to be the result of past mergers. But the details are a different story. Which specific stars from Andromeda will end up in which regions of the resulting galaxy? Which stellar systems will be ejected entirely into intergalactic space? Where exactly will new stars form triggered by gas compression during the merger? These questions remain open not for lack of effort but for a fundamental physical reason. Simulations need to choose a set of initial conditions, and small variations in those conditions lead to macroscopically different outcomes after billions of years of evolution. It is the same principle that makes weather prediction impossible beyond a few weeks, but applied to timescales billions of times larger. This sensitivity to initial conditions is not a flaw in the models. It is a genuine property of the physical system. The gravitational universe is chaotic in the precise technical sense of the term. Trajectories that start arbitrarily close diverge exponentially over time. After billions of years, the path of an individual star within Andromeda may have forked in ways that no computing power could have predicted from today's positions and velocities. Astronomy can predict the statistical behavior of the system, the distribution of stars, the general structure, the total luminosity, but not the individual fate of each sun. There is something deeply honest about that limitation. Science has not failed to describe Andromeda. Science has described Andromeda with extraordinary fidelity and discovered, within that description, the places where prediction meets its natural limits. Those limits are not walls, they are horizons. And the difference between a wall and a horizon is that the horizon recedes as you move toward it. On timescales exceeding those of the merger, the physics of Andromeda as a spiral galaxy becomes irrelevant, simply because the spiral galaxy will have ceased to exist. The resulting structure, that ellipsoid of old stars and few new ones, will evolve in ways that depend on the rate at which remaining stars consume their fuel. Stars like the Sun have lives of a few billion years. Smaller, cooler stars, the red dwarfs, can shine for trillions of years, a period so long that the current age of the universe is just a small fraction of it. The galaxy resulting from the merger will progressively become a place dominated by these long-lived faint stars, while the more massive and brighter stars go out one by one, each extinction carrying part of the system's light away forever. After tens of trillions of years, what remains of Andromeda, merged with the Milky Way and possibly with other local group members that will have been absorbed along the way, will be a galaxy of declining red dwarfs, with cores of dead stars, white dwarfs progressively cooling until they become black dwarfs, neutron stars spinning ever slower as they radiate their rotational energy, and black holes that persist because there is no mechanism to destroy them within those timescales. And then, on scales that exceed the human capacity for intuition, even scales that make the current observable universe seem like an instant, the very matter composing those dead stars may begin to dissipate. Some theoretical models in particle physics suggest that the proton, the particle making up the nucleus of every atom in every star in Andromeda, may not be stable forever. If the proton decays, and the most sensitive experiments have not yet observed this decay, but have not completely ruled out the possibility over unimaginable timescales, then the entire material structure of Andromeda gradually dissolves into radiation and lighter particles. What was once a galaxy of 1 trillion suns becomes a diffuse volume of energy spreading through space. But even before reaching that extreme scale, There is a more immediate and more observable process by which the complexity of Andromeda progressively simplifies. Satellite galaxies are absorbed one by one, the spiral arms unravel with the merger, the gas available to form new stars is consumed or heated to temperatures that prevent its collapse. The rate of new star formation drops. The galaxy ages in the most literal sense of the word, its most energetic and fleeting components disappearing while the slower, longer-lasting ones remain. There is a peculiar melancholy in this trajectory, but also an elegance. The same gravitational law that built Andromeda over billions of years is the one that joins it to other galaxies, that merges it into larger structures, that eventually dissolves its individual identity into something collective. Gravity does not discriminate between construction and destruction. It only follows the gradient of potential, always pulling mass toward more mass, always seeking the state of lowest potential energy, always organizing what was scattered into something more concentrated, and then dispersing what was concentrated into something more diffuse, in a cycle that has no director and no purpose, but that produces, along the way, structures of a beauty no intentional process could have designed better. What makes Andromeda both comprehensible and fundamentally surprising is precisely this quality. It obeys laws we understand with great precision, and yet the application of those laws to billions of stars over billions of years, in interaction with magnetic fields and dark matter and gravitational neighbours, and the expansion of the universe itself, produces an object that never stops offering something new to whoever examines it. Each instrumental advance reveals a layer of structure that was not visible before. Each more precise simulation discovers an instability the previous simulation had smoothed over. Each observation of a new wave reveals that Andromeda has a history even more layered than anyone thought. Astronomers who study Andromeda have an informal expression for this quality. They say the galaxy is well-behaved but not tamed. Well-behaved because it follows the physics. Not tamed because the physics, applied to this number of variables interacting over this period of time, still produces surprises. That combination is what keeps the field alive. If Andromeda were completely predictable, it would be a solved problem. If it were completely unpredictable, it would be inaccessible to science. What it is, in practice, is a system that offers exactly the degree of openness needed for knowledge to keep advancing without ever reaching an end. And in that openness, in that frontier that recedes as we approach it, there is a hint of something the parts of the system do not reveal individually. Each star obeys thermodynamics, each orbit obeys gravity, each magnetic field obeys Maxwell's equations. But the galaxy as a whole, considered as an entity, possesses properties that none of those individual laws taken alone can explain. There is something in the way those laws interact, in the way they combine at scales none of them was designed to describe, that produces emergent behaviour, spontaneous organisation, a coherence that seems to call for a different kind of explanation than the parts provide. Behind all this complexity, behind all these fields and mergers and orbits and explosions and timescales that exceed imagination, there is a unity that has not yet been fully named. That unity has not been fully named, but it can be traced down to a level beneath everything described so far. Below the stars, below the gas, below the fields and the orbits and the explosions, there is the level where matter itself reveals its inner composition, its chemical memory, what it carries etched in its structure since the first moments of the universe. It is the level of atoms and molecules, and it is there that the story of Andromeda becomes stranger and more intimate than at any other scale. Hydrogen is the most abundant element in Andromeda, not just in the gas clouds floating between the stars, but in every star that has ever existed, in every planet orbiting some distant sun in that galaxy, in every molecule of water that might exist on some world no telescope has described yet. The hydrogen in Andromeda is essentially the same hydrogen that exists in the Milky Way, the same that exists in the Sun, the same that makes up most of every human body that has ever lived on Earth. One proton, one electron and a bond between them that is in some sense the simplest building block known physical reality possesses. And it is from this simplicity that everything emerged. Not from a prior complexity that was simplified, not from an elaborate design executed step by step, but from a surprisingly austere rule. Masses attract, charges interact, and time is enough for these two instructions, repeated trillions upon trillions of times in every corner of the cosmos to produce galaxies, stars, planets, magnetic fields spanning 100,000 light-years, gravitational waves distorting space. The extraordinary complexity of Andromeda did not require an extraordinary number of rules. It required scale and time for a small number of rules to unfold into all their possible consequences. That is the unifying idea. Not that Andromeda is big, though it is. Not that it is old, though it is. But that bigness and age are just the space needed for simplicity to express itself fully. The beauty of Andromeda, seen from this perspective, is not the beauty of something exceptional. It is the beauty of something inevitable. Given gravity and hydrogen and enough time, Andromeda had to exist. Maybe not exactly this one, not with this precise number of stars in this specific configuration, but something structurally similar, something with that proportion between chaos and order, between formation and dissolution, between movement and balance. What this means at the molecular level is something astrochemists study with an attention that borders on delight. In the molecular clouds of Andromeda, where the gas is dense enough and cold enough for atoms to bond into more complex structures, molecules form. Carbon monoxide, water, ammonia, methanol, and dozens of other substances we recognize because we find them here too. These molecules are not curiosities. They are the precursors of what could become organic chemistry if conditions are right. If a star forms nearby at the right temperature, if a planet consolidates in the right orbit, if water stays liquid long enough for more complex reactions to happen. No one knows whether on some planet in Andromeda that sequence has occurred. No instrument exists yet capable of answering that question at the distance separating us from it. But the chemistry that would make that sequence possible is there. The precursor molecules are in the clouds. The necessary elements were forged in previous generations of stars that exploded and scattered their contents through the interstellar medium. Carbon, nitrogen, oxygen, phosphorus, sulfur. All the elements that make up known biochemistry exist in Andromeda in the proportions that would be needed. The universe, in this sense, does not seem to have favoured any particular address. It seems to have distributed the ingredients more or less evenly wherever there have been enough stars to forge them. And there is something in that thought that subtly shifts the geometry of how we position ourselves relative to the cosmos. If the ingredients are the same, if the rules are the same, if the time is comparable, then the distance between us and Andromeda is not just spatial. It is a distance between different expressions of the same physics, between variations on the same theme the universe has been performing since matter cooled enough to organize itself. Looking at Andromeda is not looking at the strange. It is looking at the familiar at a scale that makes it unrecognizable, like seeing the pattern of a fabric from far away and only then getting close enough to notice the individual threads composing it. Every carbon atom in the body of whoever is listening to this passed through a stellar core before arriving here. Not metaphorically, literally, carbon did not exist in the primordial universe. It was forged in generations of stars that lived and died before the sun was born, and scattered through space by explosions that spread their contents into a cloud that eventually collapsed to form the solar system and everything inside it. That same process happened in Andromeda. It is happening right now at this moment in some molecular cloud slowly contracting under the weight of its own gravity, preparing material for stars that do not yet exist and for worlds that have no name. Time in Andromeda continues. It does not wait. It does not pause to be admired. It keeps its slow, unwavering movement forming and dissolving, attracting and dispersing, building structures that will last billions of years and destroying others that seemed permanent. There is something deeply peaceful about that continuity, a galaxy that needs no attention to function, that does not depend on being observed to exist, that has been running its processes for longer than the human mind can conceive, and will keep running them for a time exceeding any projection we can make. And here, at this point of arrival that is also a point of departure, where science meets its own limits and acknowledges them honestly, where the physics of the parts does not fully explain the behaviour of the whole, where the chemistry of elements does not fully predict the life that might emerge from them, there is a space that is not a gap but an opening, a space where contemplation has its rightful place alongside calculation. Andromeda is still there. Right now, as your breathing deepens and your thoughts begin to lose their sharp edges, Andromeda keeps doing what it has always done. Its stars continue their slow orbits around the galactic centre. Its molecular clouds keep contracting in silence. Its light keeps travelling through space in every direction, including toward this planet, where it will arrive in a time no living being today will witness. You are safe. The universe takes care of you. Everything is in order. The stars of Andromeda do not need you to think about them to keep shining. They shine the same way regardless of who watches them, regardless of which civilization points its instruments in their direction, regardless of whether anyone at all is paying attention. There is something extraordinarily freeing about that idea. The cosmos demands nothing. It does not require contemplation. It just continues. While you rest, Andromeda continues its slow, eternal movement through space. While you rest, its stars are born and die in sequences lasting longer than entire solar systems. While you rest, its light travels. You are part of this. You always have been. The atoms composing you passed through stars. The rules governing your electrons are the same rules governing every electron in every atom of every star in Andromeda. You are not separate from the cosmos observing it from the outside. You are one of the forms the cosmos found to fold back on itself and contemplate its own existence. A local form, temporary, extraordinarily unlikely and at the same time completely inevitable, given the physics and the time. This can rest now. Contemplation can rest. Thoughts can loosen like clouds dissipating at dawn. The weight of understanding can be set down gently, the way you set something precious on a steady surface. You are here. You are whole. You are at peace. Andromeda will continue on its way. The molecular clouds will keep their silent contraction. The chemistry of the cosmos will keep its patient work in the depths of interstellar space. None of this needs you right now. All of it can happen while you sleep. Let the spiral arms turn slowly in your mind like an image that no longer needs attention to exist. Let the stars do their work while your eyes close. Let the silence of space, that deep silence that is not absence but fullness, come in softly. You are safe. The universe takes care of you. Everything is in order. The stars do not rush. Galaxies are in no hurry. The cosmos has all the time there is, and it uses every part of that time with a precision that needs no urgency to be exact. You can also have no rush right now. Breathe. The universe continues its silent dance, and we rest in its embrace. Thank you for walking with me tonight. Sleep well.